apply optimized settings. Will it work? Maybe. We'll see. But hi, welcome, one and all. It's been a little bit since I've streamed, but here I is. So today we're just gonna go over a bunch of different things. Let me lower that so there's no feedback. That was just my monitor. So here, right here. We're talking about this ICS model yet again, but more so, we're exploring the fundamental maths behind this whole idea. This whole model is just one big idea of using conservation in different aspects in a geometric way in order to simulate all different various aspects of physics, in order to relate to all various different aspects of physics, so that we can use this model, like just fundamentally as a conservation system, place relative values in their appropriate areas or use the appropriate settings in order to simulate, say, the motion of like an electromagnetic wave or a motion of some sort of attraction, whether it's gravity, whether it's acceleration, velocity, like speed over a distance. And it's more so also a way of having a system of natural mathematical units. It's a re-envisioning of math, or of time, more so. Because this is a way of also using geometry in a multidimensional fashion in order to look at these different aspects, these different attributes of dimensionality in and of itself, and how it relates to the universe. So, in starting from at least a principal foundation of mathematics, and then seeing, what might relate, what might not. This is all, again, theoretical shit. This is just a way of at least me attempting to, well, explain gravity as well as to put a lot of the ideas that I have on some sort of like solid, tangible system, right? And some way of showing, I mean, I have a bunch of projects here, but some way of showing essentially the flow of time throughout the universe. That's ultimately what this is based off of. Like philosophically, that's this surrounds the whole objective idea of the flow of time of the entire universe itself relative to its expansion. And a couple of like interesting things that I've been thinking of, at least recently, just to start off with the stream, and something that you can think of too, is when it comes to conservation, when I was looking at this model, and I'll go to the relative example just so I can show you. There's a bunch of different aspects mathematically, because initially I wanted to relate energy to the area of one of the circles and how that energy transfers from one circle to the next. Now, there was an interesting thing, at least that I've been exploring, because in this model, what is conserved, the aspects that are conserved through the translation, through the transformation, regardless of whatever the step setting is, whatever the precision that's being measured or transferred over is, basically, once this train's done doing train things, you gotta love the train. It has to always make a comeback. But basically, is this, well, for one, is this the right thing? No, this is not the right thing. This is this is versions before, man. I am looking for, there it is. So basically, when we go look at the model 2, I'll load it real quick. I have like a fresh, just one conversation with a loaded fresh copy of this version 40 now that we're in. So we jumped a lot of versions. Now this, I still need to fix to show hide these parabolas and different equations, functions that are showing. But for now, let's just focus on this, and this will help explain the point even further. Now I just want to find the relevant document, because as I've been at least working with not just Claude, but a whiteboard, using conservation from the reference of two-dimensional area, whether it doesn't matter if it's of a circle or of a square, it's that's only a factor of pi that's relative at that point to whatever difference between the area of the circle and the square that we're talking about. But the thing that really throws it off, at least destroys conservation in the terms of two dimensions, and in terms of two-dimensional areas, is the squared factor. That squared factor ultimately only leaves you with it leaves you with a quadratic equation, obviously, but it leaves you with only two real solutions where the equation's conserved and not, infinitely many, essentially, right? So that led me thinking, in a sense, that through my idea, where energy is conserved using, like, as a reference to area, they say E equals mc squared equals pi r squared, or pi a squared in reference to this model. If I wanted to transfer the energy from one state to the next, there's some distance, something has to give. There's no real conservation because there's always going to be difference. Say if you're halfway through the transition with the difference between circles, so pi a squared plus pi times a minus a max squared, supposed to equal the total area between both circles, but in a conserved way, it would have to equal the total, like the relative to the a max, right? Because say if you're trying to figure out like a maximum amount of energy within the universe, you would need some reference point of an a max in that context. But what you find is when you get to say like halfway and using this model, combination final expansion proofs might be down here. Depends on actually more so the question that I asked. But again, using the reference, you find that there's only really two solutions to conservation in that way. That means, again, if say a max is 0.5 and your a value is 0.25, so you're halfway, the radius is about halfway transitioned between 0 and a max, right? And then you do pi 0.25 squared plus 0.25 minus 0.5 squared, the negative would cancel out in that instance, equals pi times a max squared. It would be the whole area of, after it's transitioned at some point, or the total maximum that it would have. But you would find that it would not equal the a max squared value, the 0.5, because that would be 0.25 pi. Now, to keep it simple, I'll just do this in units of 0.25, or units of pi, and not have to multiply pi out. And again, this is also where you can see it when it comes to areas of squares, even. So from a circle to a square, from basically, you wouldn't say a 0-degree angle, but from curvature to perpendicular, 90-degree angle. So that little gap stretch in at least the model. That doesn't matter. That's the difference between pi and not having a digit in front of there at all. So, and in regards to the radius, the other caveat is that it would have to be 2 times a and 2 times a minus a max, because that's the caveat when you were comparing radius measure to the square measure. But even then, that 2, you can treat that the same as the pi in that case, somewhat, except the 2 also gets squared, so you get a 4. Because it has to be included in the square because it's a side length. But anyways, regardless of whatever that multiplier is, it's because of the variable where the conservation, or at least the variable in 2 dimensions, is where it kind of breaks in terms of area. But it is conserved in both perimeter and radius. because if you did the radii, I mean a plus a max minus a equals a max, it's a max equals a max, that checks out. The area is, well, the radii is conserved, the change in radii. That is conserved in the model. Same goes for the perimeter, because it's just a factor of 2 pi r. It's because it's in the one dimension that conservation can still exist, because you can take the perimeter again of the 2 pi a times, or plus 2 pi a minus a max equals 2 pi a max. That would also cancel out and equal exactly what you want, because it would just distribute over in the one-dimensional, at least analysis, one-dimensional plane. So perimeter is also conserved, but area is not. And with this model, you get to experience where that conservation comes from in terms of that p variable. Or, well, not the conservation, but you can kind of conserve it through the motion of the exchange of the radii values, or exchange of the area. And you can simulate, like, at least like the bending, the curvature of that transfer. It's weird. It's weird. But back to me searching, and instead of yapping, and then I'll show an example. The constant step size discovery. This is why I have so many different, like, radii variables. Um, Not even radii variables, but like different references, different geometric measures, all within this one model that's basically half of a unit circle in the same context of that model, just so that the side length of the square would just equal 1. And then that's a good reference point for a statistical measure. Same thing with the area of a square, because the area of the square would be 1. And that's, again, another way that you can kind of assign statistical measure in some way, shape, or form throughout the exchange of areas of the circle, because it would be relative to at least that 1 in some way, shape, or form of this area. Whether perimeter is the only fishy one, because then you would have, I mean, 4 times the side length, so you'd have 4. I mean, it would still equal as well as whatever value is on the other side, so it's technically still conserved, because again, we just went over perimeter is conserved in this model as well. Radii, both radii, perimeter, side lengths are all conserved in this model. They all follow that timeline, at least. And if I was to add at least theta warping, say if you move the timeline, say if you move the relationship between x and y, and now I'm actually starting to figure this out, then you can change theta, basically. You would have a different multiplier in front of either x or y, and it would probably have to be related to sine, cosine, and alright, that's something I'm going to explore later in my own time. That actually is a good idea. But the interesting aspect of this model, at least, is from what Claude can compile, and using Claude as more so just some way of, like, looking at all these ideas that I have never seen before, all these papers, 2025 papers, like all these different things, learning about neural networks a little bit more, learning about how, like, everything. It's just very interesting that the relationships just from this mathematical model can be made, at least through an AI compiling information based off the internet. And based off of at least Arvix for most of the references that we're getting here. So this is all, a lot of this references, a lot of these things that are being related to aspects of the model, whether it's the step size, whether it's the dimensional analysis, whether it's the dimension, like different sets of radii, the inner radii in this framework, whether it's the area, volume, any, whatever. There's different relationships that, I mean, exist that are analogous to this just mathematical geometric framework. This is just a fucking, it's a coordinate graph that runs relative to, I mean, you can either set it to the area, the volume, the perimeter, etc. There's multiple different things that we'll go over. I was also going over consciousness, so this is way too far to where I am. And I'm also kind of like Ouroborosing Claude as well, because I'm refeeding these documents and at least pursuing its compilation, it's searching with everything in mind. So linear n equals 2. I'm trying to figure, I think it was this one where it screwed up. Project file, no. It is, well, not so much screwed up. I don't know, it was the consciousness zone the one that screwed up. So that was an error that I made because I also tried to relate it to x and then give it that x equals y equals 2a, at least in this model, and then it somehow tried to conserve x and y to a max, and I'm like, no, that would be incorrect. It's actually simply 2a max in that case when you relate x and y relative to the radii. So, and then this would, I mean, this could translate at any point in that xy plane in space as a reference. So, there's a lot, and I will link this as well, just like all the other times I've friggin' linked these, so you can check it out for yourself if you have the time. I think this is the very, not the very beginning, because this is a lot of, there it is. All right. So inverse conformal geometry, and this is from the 2D perspective, and like I said with that 3D, because of that area not necessarily being conserved, you're gonna get some sort of lensing going into the z-plane regardless. You're going to get a lot of solutions that are imaginary when you're looking at the 2D plane. But what is absolute is the two endpoints when it comes to the conservation of area. So I believe this is where I at least started the whole idea. Nope. That was further right here. So it started with pi a squared, so the conservation of area, because I wanted to find all possible solutions. I did this out, obviously there's only the 2 for a max, and then the midway point is half, like a max half. That's the critical point that the mod, this is, Claude has been referencing to on this model. Again, a equals r squared, or, well, the second r. This R2, this is, eventually I'm going to replace this with B, just so it's more sensible in the context of, well, the model, and also the alphabet, too. I have an idea as well to take the bosonic string dimension, the 26 dimensions of bosonic string tension, and use that with the alphabet, because what the alphabet has 26 letters, and it's funny. It's kind of funny, because I can kind of make a loop of these in 26 ways using letters. So that's going to be one of the other implementations of this as well, is chaining instances of this model together. That's kind of where you're going to get the whole waveform and the whole gauge measurement, at least theoretically, from a model like this. And in just a statistical way, because again, you can kind of think of it in like a 2D slice, it measuring like the gauge of a wire, and you can think of like the inner circles, etc. So number of letters in the alphabet, cool. 20, yeah, it is 26. That's weird. That is a very weird coincidence, and it is actually something that I can apply. So every letter, and this would be in reference to bosonic string dimension, and that'll be, I want to see what happens with that. And obviously I can extend it and just make a second tier of letters, and it'll be in set to 26, and that'll be kind of weird, but it won't matter, because I mean it's going to be integers by the end of the day relative to integer distance. Maybe I have ideas. I have ideas to how to implement a bunch of different aspects, but regardless. So the ICS inverse of distance is always less than or equal to -1. Yeah, because this is the displacement between radii, where R2, and just to go over, R2 is relative to a max minus a, so it's the inverse of that second circle. Now, let's go look at the circles, so you have a better idea while we're here. And do a little bit of that. I just want the play button there. Turn that off because I don't use that. All right. So this is the idea. This is the radius. You see the one. You can see the grid line that makes up the square. I can also add in the squares, but this is the idea. The radii dictate the range of motion of this relative to a step size factor. The step size factor is relative to at least numerations of 10. And the reason why I did that is because when we measure in scale, when we measure anything in scale, this was actually a video that Hank Green actually did uh, recently, a little short, was that when we count like our digits, our integers, when we get to after 9, it just repeats 1 0 and you kind of like tally it over. It's the same thing with precision when we do measurements mathematically in that regard when it comes to decimal places. So the design of the step size factor in and of itself is a way to relate that depth of precision with the tens place and how, I mean, our mathematics, our system of mathematics utilizes sets, right? Sets of 10. And that's relative to decimals and everything else. And that is essentially how motion, because even when we go to higher and higher precisions, ultimately that changes the acceleration as well as the velocity of change, depending on the system that, I mean, is being transferred. But it also depends on the mathematics behind what's being transferred, et cetera, et cetera. So the initial step size hierarchy, h of p, that's the function, equals h naught times 10 to the power of negative p. This is important, the negative, because this essentially places an inverse on the decimal. So instead of, and it's not like, you can't really say square root. Square root would be 1 over p if you wanted to emulate a square root in exponential form. But in this instance, I'm actually using this in order to move the decimal place over this way to the left because of that negative. So instead of it exponentially, it's basically logarithmic. That's what the negative does. It turns it into a log, right? And that p, using the idea of the inverse square law, where, I mean, double the distance, a quarter of the power, it's, when we think of physics, and not even just physics, but mathematics and how mathematics relates to describing physics, when we talk about energy, the movement of pure energy being energy is massless, that would be photons, be gamma rays, UV rays, etc. Those heavily rely, not even heavily, their power level over a distance in the vacuum of space itself follows the inverse square power law. That is how we measure it. So taking that idea, again, if I wanted to do area conservation in some way, shape, or form, I would have to do it in terms of precision. How the rate at which that energy is, well, changing, being dumbed down logarithmically, and that's where we can get kind of funky. And that's just the standard. The I is just a power scale factor. So I referenced Planck, and well, I think it was like the maximum amount of scalable size energy, or maximum amount of scale that we can measure it one around the power of like 10 to the 123. Like theoretically that might be the maximum amount of energy in the universe, so I kind of just stuck with that. Obviously I can do whatever with this model. I can expand that to like almost infinity if I want, but then you're going to have time scales that are insane. Now, the reason why it's lagging is because this is doing a lot of calculations on this panel. So when you use this and when you experiment with it, I advise to do your settings. It can be a little bit less choppy, because this is like a 3 megabyte fucking model. There's a lot, and there's a lot of other different measurements that are like at least have been compiled that are measurable. That are there's animations and stuff. There's a bunch of cool little things you can check out. It'll at least get you thinking of like visually how a lot of these aspects are measured. A lot of these things are like understood and calculated without like a definite like reference. So it's just statistically in the model, but you can see it's kind of choppy. Let's pause it. I do want to put like a space bar to pause on this, and I will switch this to an HTML as well and have this on my website at some point. So going down to that, you can change that P, you can make it relative to multidimensional area or multidimensional volume, perimeter. I added a bunch of different ways, and there's still more I need to add, and even like 2 times. So again, like that two. Yeah, because it's all in the brackets. Yep. I was very careful with a lot of my bracketing and a lot of my parentheses to make sure that things actually were mapping out correctly. All right, besides that, we had that h naught. So remember, it was h naught times 10 to the negative p. That would be the negative p factor. So the rate at which the precision decline, or well, improves or declines, rather. The h naught is just an initial step factorization. I can just do it equal to 1, and it would be purely relative to that, but then you're going to have some breaks at certain points in the model. I mean, thankfully, since the radii is already at 0.5 starting, because that's what you're going to be multiplying anyways, because again, it's using a half-life idea and using geometry in order to measure this, so 1 could be acceptable. Amax is also another acceptable multiplier. That HP, by the way, gets multiplied by A of P in the NP section. So if I can find, remember where N of P was. This was also just the basic measurements of each circle. All right. Linear equations. These are the 2 lines, the 2 timelines. And when I wrote at least the timelines, I included pi, like these various factors, so that, I mean, it would equal this essentially, where a is relative to x plus y, and that would be the timeline. So, and I kind of tried to do it as well with equation of a circle, etc. So interesting stuff there. Yeah, hyperbolas as well. Random matrix, theta spectrum. This is all different theta points. I have a bunch of different modes measuring different theta aspects. So like arctan. This I still need to tie more into because I want to turn this, or at least tie this into something that rotates and affects the cosine. Like I was just saying earlier, the x and y relationship. Because with this, then if there was like a cosine of this variable and then a sine of this variable, we're gonna get warping, and it's gonna be symmetric. And it'll be related to A again, or not even just A, but the neighboring framework. So not the A minus A max, but the A max minus A, which will be over here. That is, at least, say if we want to do iterations of this, that's how it's going to look like as well. Where you're going to have this, and then this is going to basically mirror over to here. Kind of, well, not really. This is going to be, this will be connected to this, so it'll be the opposite here. These two, it'll kind of flip. And then you'll get this over there, and this is where you're going to get waves. And then this is how it's going to relate to, because if this is big ampy goes back down, you can kind of envision it, so waves stretch, and you can think of it in terms of a set like this. And then again, you would also have it like this as well, and you have parallel, and then this whole framework is basically a bunch of these fucking circles back to back, right? And you're gonna get two perpendicular fields. And then with a rotation, you can get basically like interference, etc., etc. Cool things, cool potential. Like it's maybe simulating particle paths or particle wave duality paths. Is a bunch of different mathematics that at least get you thinking and imagining like different approaches to a lot of these problems and aspects of quantum mechanics and physics that we might not understand fully yet. So, yeah, born, going back to this, I'm trying to remember where my NP factor was. Down here, I think, right? N, A over H, so it's n to the power. Yeah, log HP. That's interesting. HP. P active. Yep, because I have I 0, so that's effective area. H naught. Where is the formula? HP formula. P formula. NP step hierarchy. Yeah, this is how NP equals A max over HP. That's the basically A. That's NP times A equals this. That's what's determining A. So NP anima on. I'm gonna check that out, and I'm going to do a multi-dimensional. I was doing one the other day. It was really cool. It had like a nice like spring effect. It was emulating spring tension, pretty freaking cool, honestly. Like really, like really accurately. To the negative n+1. Yeah, upper dimension. So the n is the dimension that's being measured. And so, say if I wanted to simulate this and activate, I just do 1. I also have fractional, so you can kind of get like a faster version, bigger acceleration. I have to get off of this tab though. Yeah, it's kind of like a spring. It's not as smooth as the other one was, but it's kind of a consistent rate. Huh. And then the P. Sorry, this is just quick options for when you see the areas with E in the step size factor. So you see the pi E squared. That's what it's referencing to. That entire function. When you see A and A max, these relative, which is you would think is kind of a conundrum, but it's self-feeding in a weird way. So that value of A that's calculated is then fed constantly back into the model. And it is constantly counting on itself. This is where this model isn't based off time. The frame rate itself, yes, it's based off time, but the motion is based off itself. The time it takes for that revolution to complete is based off itself, some factor of itself. And that's what makes this, mathematically at least, time independent. But it follows a flow of time. It can simulate a flow of time using these different factors. So, now, I think the one that I was doing the other day, or yesterday. So these are the C of n, that's the gamma function for the circle. The A of n would be referencing volume. The ones that are n-1 with the n, those are multidimensional surface areas of a circle. So it's basically, it's the derivative. That's, again, at least multi-dimensional analysis using the gamma function and take the derivative, I mean, relative to n, which would be the dimensional power of a volume, you get its perimeter. And that's where you can get relationships to gradients as well as some vectorization. There's some vectorization as well that I want to implement. That's why I at least have this project up. And that's also why when you look at the project, it's 100% full. A lot of these are just compilations of a lot of the different factors that are in this. And the model itself is 51,682 lines of code, all compiled with all these different like references to like Midgall when it comes to quantum and classical gravity. Navier-Stokes, was it John Longfellow who wrote a paper as well. I implemented some of the equations from there under this model, and that's where all those extra panels are coming from. There's just different coupling measurements. Well, using this, what at least has a reference within this model that from Claude's reference as a Turing model. So, yeah, Morse critical, Morse critical, no, critical point at A star. A star, I think that's the halfway point. And derivative f of A, yep, that's the perimeter, so let's go in there. 0 has no solution in 0 A max, however, restricting the ICS constraint and considering equals, yep. So this, I actually worked this out on the whiteboard as well. So this is where conservation is weird. But yes, the critical point, A star, A max over 2. A max over 2, that being a critical point, is basically, it's another way that you can get somewhat of a solution. Kind of. I mean, well, you get a clear over 2 value because you're halfway. You're at the median. You're at the, basically the maximum of the quadratic function, or the minimum, depending on the type of relationship that you're using for your precision. Complex holomorphic number theory. So the k, yep, n-ball coefficients, the c of n, that's the gamma function like I was just stating. It just simplified the c of n, interestingly enough. So, you know what, I'll keep it. And then the np, yep, so it's the step factor, the Zipf law from inverse symmetry. So we get the 1 over z, and this is why it also kind of relates to Riemann's zeta hypothesis, Navier-Stokes turbulence, the mass gap as well. There's a lot of different things that this model can relate to and potentially explain. More so, again, like with that wave function that I was talking about, neutrino mixing, this is what I'm interested in, is the phasing of neutrinos. Because I feel like that displacement, that, and when we look at distance, and this is the other thing where maybe this is why general relativity does not work with quantum mechanics, and at least a more intuitive sense of thinking about it is when we again measure E equals mc squared. I mean, it's analogous, extremely analogous to pi r squared. It just in form, or the 2. Well, you can't even say the 2a squared because the pi would technically get squared in that instance. So it's more analogous to the area of a circle equation. But conservation applies to E equals mc squared. It does not apply to area. But where conservation does apply to is the change in radius, the distance of the radius, and the perimeter, at least the what's bounding that area, what's causing that area to be bound. But in terms of general relativity and what we experience, I mean, energy is conserved, but distance in reality is not conserved. We can go from point A to point B and not spring back. And I think that tends to explain, at least, I mean, space itself, just in a more intuitive sense, why we can move from point A to point B in space. Why are we able to do that without, I mean, there's gravity exists, and that's probably the only force that's conserving distance. That is your only real conservation of distance, is gravity. And that is through relativity based because of mass. because gravity only exists in objects with mass, and that's relative to E equals mc squared. And that difference right there, that's where things relate, but mathematically we can't seem to just have one simple equation that dictates that. There seems to be this inversal relationship, which this ICS framework can model and at least kind of show in a derivation or a derivative sense. Because we're not measuring the manifold of space-time itself, but rather the change in space-time. We're measuring the change in the expansion of space throughout time. As time, I mean, the flow of it, there's time dilation that we have measured. There's those phenomena as well when we get to the extrema events of like black holes, where mass density is so large that it breaks Planck luminosity, and because it breaks Planck luminosity, therefore, I mean, there's a lot of fundamental forces that just break simultaneously past a star's point of nuclear fusion. And with those phenomena, I mean, they have their own timeline basically when it comes to black holes, especially with evaporation. As I mean, technically, its lifespan gets inversely expanded the more stuff is near it, the more mass is near it, as it consumes, as it, gets bigger or destroys everything in the event horizon, and then energy is transferred and temperature is transferred, etc. A bunch of weird things happen relative to Hawking radiation and stuff like that. Relationships in that context, but it's indicative to, I mean, this model as well. So another few aspects of this model, I mean, this Higgs VV from ICS geometry, unit conversion needed. So there's a bunch of different things. Actually, that is basically the next step, because I'm trying to figure out the relationship between neutrinos and the Higgs mechanism, and understanding the extreme circumstances where the Higgs mechanism can break, or, well, I mean, with neutrinos, it phases in and out. It's like the neutrino is skipping, because it loses mass, it gains mass, it loses mass, it gains mass. It kind of winds down as that energy is distributed throughout space. There's some weird relationship with the Higgs and neutrinos compared to all the other particles. Will, they'll swallow the Higgs boson, whatever, they'll combine with it. Neutrinos, they're weird. So that's the minima. The maxima is the anti-Higgs postulate, which is in extreme exotic circumstances, things become so big. I mean, it is also kind of relevant to neutron stars, black holes, but even more so at the very, very beginning of time, toward energy levels nearing the Big Bang, is where you get some weird exotic mathematics going on with the Higgs field in the maximum sense. So I was able to at least establish those 2 points. But now I need the unit conversion. I need some way to do that. I also have at least have some theoretical energy measurements of a particle. Like, I wouldn't say a graviton, but it's more so relative to, I think, dark matter, and, well, dark energy more so. Dark energy particle. But that is very theoretical, but it would explain the mass gap in some sense, and maybe they'll also explain the blackness of space or something. I don't know. Actually, there's a bunch of other stuff that explains the blackness of space, but yeah, it's a lot of math. It's a lot of different aspects and a lot of, I mean, equations and things that I've just haven't been looked through. It's a lot. But the cool parts too, with at least the multi-dimensional stuff, the math stuff is at least the most integral stuff of the model. It's just a coordinate graph that has these relationships that there are some guards at the end in the code, but otherwise there's no other guard. There's no need for anything else. Like, this model just calculates. I mean, it's just math, geometry, shapes, different aspects. So there's also, besides circles and squares, there's also pyramids and triangles that I'm trying to interpret into here. And there's also Wallace product shapes as well. Oh yeah, shit. There was, yeah, that went missing. In one of my older models, there was the math, but this is actually kind of good. I'm kind of glad that it went missing. But there was a math domain, and not this cross domain. This cross domain has a lot of different measurements and just theoretical values, winding factors, etc. But there was one that had Euler's number. This is the walls. There's these ones here. Yeah, Fourier, Taylor. So some of these did get swallowed up by other things, but there was one where I can do a Fourier transform on the 2D. All these different linear combinations, so I might have to bring that back, which like I have the older models saved as well, so I could just kind of take the code from there and just put it back in, so that's fine. Because I do, but I also do kind of want to re-implement it from the ground up and redo the tabs. There's still a lot more optimization, like I said, that needs to get done with the model, because Claude is only good at so much, and obviously you can't fully rely on it, which, I mean, good. Which is why I'm also looking and researching and learning about a lot of these different things. Cause what the hell is this, right? What is this? Spin foam. So then I just do this. Boom. Casting loop quantum gravity. Oh, loop quantum cosmology and spin foam. So, and then I can learn. But it's not like it's pulling from bullshit. So interesting. Wikipedia. Spin foam models is to provide viable path integral formulation of quantum gravity. Because of background independence, their underlying framework has certain novel features that are not shared in the paths of the Minkowski space, which is what this whole thing references, LQC. So all these different aspects are in there, and avenues the Hamiltonian approach. Led Feynman the years do Miguel gravity. Oh, it's if I can put gravity in the names of their emails, the sign. It's FMs. Determine transition amplitude for the first state, specified at initial time. So these are measurements that are based off time. Discrete sum. Where are the equations? Here. Alright. Focus on simplest LQC model that has been analyzed and detailed. K equals 0. Lambda equals 0. Friedman model. Massless scalar field as a source. However, it should not be difficult to extend this analysis to allow for a non-zero cosmological constant. Okay. Spatial compound. Spatial manifold S topologically R3. So in the real 3-dimension Cartesian coordinates, x to the power I theron, and a fiducial metric QAB given by QAB dx to the power of A dx to the power of B equals dx squared, dx1 squared, dx2 squared, dx3 squared. Physical 3 metric QAB is then determined by a scale factor A. No, no. For the Hamiltonian analysis, okay, that's very interesting. That is interesting. Fucking scale factor. Yeah, again, it's A is cubed. Okay, so physical volume, AQV naught. Yeah, yeah, it is. Yeah, it's fucking okay. Geometry V equals 2 pi. Yep. Turns out to be convenient configuration where the gamma is Barbero and moons a parameter. Kinematic typical Hilbert space is a tensor product. Yep. Kinetic gravity, the matter, the relationship between gravity and matter. Gravitational matter, Hilbert space. Yep. Elements. Yep. Point countable number of points with finite norm, and the absolute value of phi squared equals the sum of v by v, or function of phi v squared. Matter, Hilbert space is standard one. Hilbert space kinetic equals L squared, real number domain, times d. What is it, lo-fi? I believe. Squared? Or is it just a second point? Thus, the kinematic quantum states of the model are functions with finite norms. Jesus Christ. Yeah, so this is the derivative of b, derivative of phi, and the bracket notation relative to, or the bra would be that, and the ket would be v phi equals partial derivative of the matrix. What was that? The matrix v derivative that. Is that no? It's yeah, it's still more I'm learning. Okay, but it's in the bracket notation. So then you're gonna have your spin factors, etc., etc. Quantum constraint can be written as negative c phi partial derivative squared phi, or from no, phi to 2. Zero. A self-joint operator on Hilbert gravity kinetic. More explicitly, it's not theta. What it's kind of like theta is the second order difference operator. And then we got gravity in here. And we got square root v plus 4. Okay. It's oddly relevant to. Well, does this square root only affect the absolute value? Okay. And this is multiplied? Plus. I'm assuming because that has the brackets there. Should be closed off. This is raise area gap. 4 pi square root 4 root 3. So this is in 3 dimensions. So you get the 4 root 3. You get 1, 2, we get the minus. Yeah, because you have 1, 2, you have the 3 dimensions here, and this is basically like kind of relative to that z coordinate that I have from like the 2-dimensional plane. It's weird. At the space solution, so the quantum constraint can be naturally decomposed in the sectors in which the wave functions have support on specific v lattices for definiteness. Okay. We will restrict ourselves to the lattice v equals 4 and L1, where n is an integer and relevant to dimension. Details of the expression won't be needed for most of our analysis. Scalar field, lo-fi, monotonic on all classical solutions. Okay. Then the integral of d of k, 1 over 2 pi, integral of d of p, lo-fi, f hat, is that an f? Looks like an f, yeah, it's an f. No, f with the tilde looking ass sign. Kp, then it's Euler's formula. Roll negative infinity unless otherwise stated. Using this expansion, we can group any average function of v and phi to obtain a distributional solution. Okay. Phi. Let's formula the operator. And then we have phi plus minus. Alright, so now I'm going to go back to my model, now that I've read this. A to the power I of A equals what the fuck? World connection. Gamma k I, sum of gamma there. Okay. Interesting. J light. Spin foam log. Yeah, pi root 3, that's there. Okay. Gravity coupling. Huh. It does stuff. What if I do this? Did not change anything. And it changes the rate that this changes. That's for sure. If I change these, doesn't change anything necessarily there. Hmm. This is very interesting. Tropic gravity. Yeah, it's gonna take me centuries just to go over all of this stuff. Jesus Christ. So negative frequency solutions to with respect to the relational time phi. True solution. Hmm. F. It's timeless framework. One works with a timeless framework because the natural deparameterization is not available in general to mimic the general spin foam constructions in LQC. In this section, we'll largely disregard the fact that the scalar field can be used as relational time and that the final constraint has the foam of the Schrodinger equation. Instead, we will use the group averaging procedure for the full constraint. C equals negative partial derivative by 2 or squared. That's that equals P. Okay. So you just change that. Okay. Oh, change it to a positive. Okay. Time instant. Kinematic states. Some more bracket notation. And the average solutions. Okay. Vertex expansion. Alignment and then rearrange. Wow. Some of our histories. Belly. I did see some of this stuff as well. Kinetic matter, kinetic gravity. Amplitude AG is not as simple. Versus some of our histories. Gravitational amplitude A of G. Some of the series, etc. Bracket notation relative to Euler's number. Hmm. That's interesting. So I'm still curious as to what aspects, but I think more so I need to be able to define phi and because it is getting these numbers at least from within the model. And let's see. To do a Feynman diagrams. They don't really do anything. Oh, it's actually moving wicked slow though. I just realized. Do this. Uh, did I change this? No. Huh? Oh yeah, I did change this. Nope. Don't. And yeah, because I did this perimeter over the area, or the perimeter more so of second circle over the area. Okay, so that's why I'm getting that very, very big slowdown coming that way. And this is if it was R2 relative instead, which most dimensions won't really matter. Bro, go this way. Thank you. It's mad at me. Oh shit. Oh, what we got? It's speeding. It's speeding up. And slow down. Yeah, again, it doesn't do anything in the context of this. Speed it up. 4, 8, 9, 11. And then I doesn't do anything. Oh yeah. Wait. No. Wait a minute. It does do something? Okay. Should have a times I, right? Oh, it does not. Wait, what? Oh no. Oh yeah, it does. Okay. I was about to say, yeah, it should have a times I. That's weird though. Well, that's it's like no matter what scale I go to, it doesn't really slow down or speed up. That's an interesting relationship there. Okay. What if I did the area of the circle over the area of the square? Should be basically like a just pi clock at that point. But well, the gamma function makes this weird because this is in 2 dimensions now, but in 1 dimension. And let me go back to the 2D looking ass graph because I don't even have the spears. All right, cool. It's kind of a constant rate, isn't it? Slowed it down, okay. Dunk, dunk. Yeah, it just leaves like the gamma function by itself, and then that controls plays pace. Huh. From here, same speed. Okay, from here. Same speed basically. Yeah, and then these two don't make a difference. Just creates lag. Eh, huh. Yeah, I mean, I was you just have a factor of 2 there basically, and that's like no, a factor of 4, and then that would cancel out with the well the 4 times. So if I multiplied I by 4, and then that would cancel out, and that would just be a gamma clock at that point? Question mark. Okay, let's see. Oh, and again, I have this precision factor as well. I gotta remember that's also slowing this down because every time I go up an n, this is like another decimal place over. Is that minus? Let me make some of these bigger. Again, it's the minus n. Let's do just h naught to the 1. Can I get away with that? I can. The animation breaks further up you get there. Oh, and this is the cool little doink. So that's a cool effect. Now we're not getting the bouncing anymore. We're getting it's restarting from the beginning. Nope, I gotta do stuff. Yeah. Oh, what's up? Yeah, I sent it. I said a rep is gonna get back to me within the next 3 days. Alright.